next lecture of quantum mechanics. So in today's lecture, we'll see the derivation of Schrodinger equation. So when we talk about the quantum mechanics, it is one of the most important theories in modern physics, and at the heart of that theory, there lies the Schrodinger equation. So Schrodinger equation plays the same role in quantum mechanics, like Newton's law plays in the classical mechanics, and Maxwell's law plays in electromagnetic theory. Whenever we want to study a quantum mechanical system, whether we are interested in finding the linear momentum, kinetic energy, potential energy, or position, or other overall behavior of microscopic particles, the starting point is always the Schrodinger equation. So this equation allows us to describe how quantum particles evolve and behave in different physical conditions. So the idea of this derivation of Schrodinger equations came from the de Broglie's hypothesis. Basically, when Schrodinger in late 1925, he was giving a talk on de Broglie's hypothesis, and basically de Broglie's hypothesis tells us that if a particle is in motion, that basically behaves like a wave. And then Schrodinger started thinking about if a particle is in motion and if it behaves like a wave, then there must be a wave equation associated with it. So if you see the de Broglie's hypothesis, like here you can see it. So when we talk about de Broglie's hypothesis, it tells us about if a particle is in motion, then there will be a wave associated with it, and that wavelength of that particle will be in the relationship with the momentum of the particle, right? So if you see here, so lambda will be equals to h divided by p. So this is how the wavelength of the wave that is associated with the linear momentum. And then Schrodinger took it very seriously and went back to his work. And early 1926, he published a series of papers while deriving this Schrodinger equation. So the idea was, let's say if you have a wave like a standing wave, the equation of a standing wave looks like that: del 2y by del x square, that is equals to 1 upon v square del 2y by del t2. And here you can see that if we plot this wave like that, this is the displacement along x direction, and this is the amplitude. Sorry, wave equation. So something like that. This wave will look like in this way, right? So the maximum value of this wave magnitude, that is called as the A, that is called as the amplitude. And if you see here, so this will basically look like that, and this is called as the wavelength, lambda, right? And if I want to write the solution, let's say if I am assuming this one is our equation first, and if I want to write the solution of this equation 1, this equation's solution can be written as y equals to a e to the power I kx minus omega t. So we will see what is the value of kx and omega. So basically k is your wave number and omega is the angular frequency. Is that clear? So let's try to understand if we derive this equation. Let's say if any in complex number we can expand this function e to the power I theta in the form of cos theta plus iota sin theta. So similarly we can expand that. It can be written as y equals to a cos kx minus omega t plus obviously iota sin kx minus omega t. Right? We can write like in this way. Okay. So now, if we want to derive the way Schrodinger derived this wave equation or Schrodinger equation, so there are some assumptions that he has taken care of that. So first assumption was that, let's say, in order to derive this equation, so the assumption was, first assumption was it should be consistent with the de Broglie's hypothesis as well as Einstein photoelectric effect. So let's say if I am talking about de Broglie's hypothesis, so it should be consistent with de it should be consistent with de Broglie's hypothesis, and de Broglie's hypothesis basically tells that lambda equals to h divided by p, where wavelength is in relation with the momentum, right? And from photoelectric effect, we can see, so it should be consistent with both of these, sorry. So B will be the photoelectric effect. So from photoelectric effect, we can see that energy can be written as E equals to h nu. So I will divide this as h divided by 2 pi and then multiply with 2 pi in this equation. So h divided by 2 pi can be written as h cut and 2 pi nu can be written as omega. So from here we can calculate energy is h cut into omega. Is that clear? And from here we know that lambda equals to h by p. Okay. And from here we can say that wave number is equals to 2 pi by lambda, where k is the wave number, right? So now here what we can say that we will substitute the value of lambda 2 pi. Lambda is equals to your h divided by p. So that can be written as p divided by h by 2 pi. So this can be written as the value of k can be written as p divided by h pi. So from this equation, from de Broglie's hypothesis, we got the value of k, and from the photoelectric effect, we got the value of E. Now we will substitute this value of K and E in our equation. So as we have seen that the solution of wave equation was like y equals to a e to the power I kx minus omega t. So I'll substitute this value of k and e omega in this equation, and we will get y equals to a e to the power I, and k will be equals to your e by h cut into x minus omega is equals to e by h cut into t. So finally we can write this as y equals to a e to the power I by h cut and then ex minus et. Right. So finally this is our solution of wave equation. Right. So this is how the solution of this wave equation looks like. Okay. So now we assume, since this is the solution of wave equation, that means that is the wave function, right? So this will be called as psi of xt, and that can be written as your obviously a e to the power I by x squared px minus et. So wave function is just a mathematical function. It does not contain any physical observable or measurable quantities like linear momentum, kinetic energy, total energy or position. So in order to calculate the observables like properties, physical property, we have to operate some operator over the wave function, and this wave function basically will give you your kinetic energy, linear momentum, position, all of these values. Is that clear? Okay, so we'll see these things later on, but our goal is to derive the Schrodinger equation in this lecture. Is that clear? So let's try to understand how we can derive this equation. So now we have this wave equation, something like that, psi of xt, that is equals to a e to the power I divided by h cut and your ex minus et. So if I perform the derivative of this psi with respect to x, that will give you a I divided by h squared, and then it will get multiplied with p, and it will give you e to the power I by h, as it is px minus et. Is that clear? So here you can see that a into e to the power I by h cut px minus et is psi. So that can be written as del psi by del x, that is equals to a I by h squared p psi. Is that clear? So again, if I do the derivative of this, let's say this one is my equation first, this is my equation second. So if I again differentiate equation second with respect to x, so I will be getting del 2 psi by del x squared, that is equals to a So that is I by h squared whole square p square, and again you will be getting e to the power I by h squared px minus et. So basically a into I by e to the power I by h squared px minus et is psi. So again I can say that del 2 psi by del x square, that is equals to what? Minus e square by x squared psi. Right? So we have got the value of del 2 psi by del x square, that is your minus p square by h squared into psi. So from there we can write that minus h squared del 2 psi by del x square, that is equals to your p square psi. So let's say I am assuming this one is my equation 3rd. Okay. No, so we have got the value of p squared psi. Next, we have the wave function equation is like psi of x3, that is equals to a e to the power I by h squared and then px minus et. So if I do the differentiation of this equation with respect to t, let's see what will I get. So if I perform del psi by del t, so I will be getting a I by h squared minus e to the power obviously I by h squared px minus et. So a and e to the power I by h squared px minus et will be called as psi. So I can write del psi by del t, that is equals to minus I e by h squared and psi. So let's try to rearrange this equation again. So I can write that minus h squared divided by I del psi by del t, that is equals to e psi. So in this equation, if I multiply by I in the numerator and denominator, I will be getting minus I. So I squared will be minus 1, so minus minus will be plus I h squared del psi by del t, that is equals to e psi. So I'll assume this equation is my equation 4. Okay. So till now we have derived the value of p square psi and we have derived the value of e psi. Okay. Now, second assumption was when Schrodinger was deriving this equation, the second assumption was the total energy. Here I write that total energy, that is equals to obviously kinetic energy plus potential energy. Is that clear? So total energy which I assume is E, that is equals to kinetic energy is obviously from classical values P square by 2m plus potential energy we can write as V. Okay, so if I multiply this equation by psi, so it will give you like E psi, that is equals to P square divided by 2m psi plus V psi. So let's say I'll assume this equation is my equation 5. Is that clear? So in equation 5, I'll substitute the value of p square psi and e psi, and let's see what will I get. So I will be getting e psi will be equals to I h squared del psi by del t, I h squared del psi by del t, and what is p square by 2m? That is equals to minus h squared. So that will give you minus x squared divided by 2m del 2 psi by del x squared plus v psi. I hope this is clear to all of you. So this is just a simple mathematics, and we have derived the Schrodinger equation while assuming at starting we have assumed there is a wave equation, and from that wave equation solution we have derived the Schrodinger equation. And in this equation you can see once you solve this equation, this will give you the value of psi, which is x and t, that is a function of x and t, and that psi is not just a mathematical function. It does not contain any physical property. So in order to extract some physical property, you have to perform some operations like linear momentum operator, kinetic energy operator, position operator, and once you operate these operator over this will give you the observables, that is the visible physical quantity in the quantum mechanics. Great. Now, next thing is that we have to solve this equation, right? So for various kind of problem in the quantum mechanics, we have to solve the Schrodinger equation based on the boundary condition. And how we can solve this, this Schrodinger equation? Let's say if I assume this is my equation second, and in order to solve this equation 6, we have to use the separation of variable techniques. Why? Because here you can see psi is a function of space and time variable. So this is just a second order partial differential equation, that is a linear partial differential equation. And in order to solve this equation 6, we can assume. So here we'll start with the solution of equation 6. So here you can say that this psi, that will be a function of psi x and phi t. Is that clear? And once we substitute this value in equation 6, we will be getting IH del by del t of psi into phi, right? You can assume, you understand if I am writing psi, that is function of x, and if I am writing phi, that is a function of t, and that is equals to minus h square divided by 2m del 2 by del x square psi into phi, and then plus v into psi into phi. So here you can see that phi is a function of time. Psi will come out of the integral because with respect to time, psi will be constant. So I can take psi I squared del phi by del t, that is equals to minus h squared divided by 2m, and here phi will come out of the integral, and that will give you del 2 psi by del x squared plus v of phi into psi. So if I divide this equation by phi and psi both sides, so I will be getting this value, like 1 upon phi. So I h cut by phi del phi by del t, that is equals to minus h squared divided by 2m into 1 upon psi, and that will be del 2 psi by del x squared. Is that clear? Plus v. Is that clear? So now, if this quantity has to be equal, then it has to be equal to some constant, let's say c. Is that clear? And now you can see that we have, converted this partial differential equation into the two sets of ordinary differential equation where phi is a function of time, psi is a function of space, and both of these will be equals to a constant psi. And then we can solve this ordinary differential equation, and we can get the final solution for the Schrodinger equation. So I'll only solve this part in this lecture, and the second part will solve in the next lecture. So here you can see that 1 upon phi, that is I h cut. Now you can write here, this can be written as d phi by dt now, right? D phi by dt, that is equals to constant. Is that clear? So this can be written as d phi by dt. That can be written as now c divided by I h cut phi. So if I multiply with I on numerator and denominator, this can be written as d phi by dt, that can be written as minus I psi by h cut phi. Is that clear? So if you solve these things, then you will be getting phi t, that is equal to, let's say I am assuming a constant a, and e to the power minus I c by h cut into t. So now this is the time dependent, part of Schrodinger wave equation, which is a ft, phi t, right? So I'll stop this lecture here only. In the next lecture, we'll solve the time independent part, that is this one, and we'll see how we can solve these things. And after that, we'll start the problem based on this, like, we'll solve problem based on like particle in a box in 1D, particle in a box in 2D, and then we'll switch to the hydrogen atom. Okay, thank you. See you.